Welcome to the first lesson in chapter 2. In this chapter, we'll be dealing with geometric proofs. So we're going to get some like vocab terms, definitions in for the first couple of days before we start actually writing our proofs. So the big idea for this lesson is postulates, or sometimes they're called axioms, but I usually use the word postulates. Postulates are just math rules that are accepted as true without proving. They're kind of like common sense things that everyone knows. And then we have theorems. Theorems and postulates go hand in hand because theorems are also math rules, but these are math rules that someone has already proved. They could have been proved using postulates or definitions or undefined terms. So theorems are just rules that have already been proved. All right, so today we're going to learn 7 new postulates. Again, postulates are things that in the math world we just kind of accept without proof. So even though we're learning new things, as I reveal these, you're going to realize that you know most of these facts already. So our first postulate says that through any 2 points, there is exactly one line. Every single postulate is going to have a name. So for example, this is postulate 2.1. You don't have to know the names. I'm never going to read you a postulate and ask you what number it is. You just have to understand that postulates are things that are accepted without proof. So if I were to give you this postulate with one word missing, you should be at a point where you could fill in the blank. So if I said through any blank, there is exactly one line, you should know that that blank is 2 points. And then I just got a picture showing us that if I have 2 points, then there's a line that I can draw between them, and I really only have one choice for a line to connect those 2 points. Second postulate in this lesson, through any 3 non-collinear points, there is exactly one plane. So we're just taking that last postulate and we're kind of adding on a dimension. You can see I've got an illustration. If you have 3 points, let's call them A, B, and C, then you're able to draw a plane through them, and you've really got one choice for the plane that you can draw. Third postulate, a line contains at least 2 points. So if I have a line, then I'm able to add 2 points to it. You could add 3, 4, 5 points, but if you've got a line, there has to be at least 2 points there. Next one, a plane contains at least 3 non-collinear points. So a similar idea, if I've got a plane, then I'm able to add 3 non-collinear points to it. I could have more than 3 points, but at minimum, in order to have a plane, you need to have 3 non-collinear points. And just because we don't draw points on the plane doesn't mean they're not there. Postulate 2.5. If 2 points lie in a plane, then the line containing those points will also lie in the plane. So I've got an illustration. If I've got 2 points in a plane, in this case my points are A and B, then when I draw line AB is also going to be in that plane. I think we've got two more. So 2.6, if two lines intersect, then their intersection is exactly 1 point. And then 2.7 takes that and adds another dimension to it. If two planes intersect, then their intersection is a line. So again, maybe some of these feel kind of new to us, but in theory, these are things that everyone who knows geometry accepts as true without proving them. So even though they're new, you probably were kind of familiar with these ideas already. All right, now we're going to go ahead and find some examples of each of these postulates. So looking at some pictures, I want to state the postulate that shows each statement is true. Statement A, line W and line P intersect at exactly 1 point A. So my postulate would be that where two lines intersect, there is exactly 1 point. If this were like a test or a quiz, you would just write out that postulate word for word because you probably don't have the numbers memorized, and I don't either. But since we can just flip back and find that postulate, let's do it. So I'm looking for if two lines intersect, then their intersection is a point. And I find these really fast just by looking at my pictures off to the side. So that's postulate 2.6. Statement B says through A and B, so those are points A and B, there is exactly one line. In this case, that line is W. So I'm going to go back and look at my postulates and look for the shortcut that says if I have 2 points, then I can draw a line through them. It looks like it's that first one, postulate 2.1. Statement C, line W contains at least 2 points, A and B. So this is kind of the opposite of that last postulate. If I've got a line, then I can add 2 points to it. That looks like it's postulate 2.3. Statement D says points D and E lie in plane R, so the line that contains them also lies in plane R. So I'm looking down at this picture. Plane R, I've got two planes overlapping here. So this one is plane R. D and E are inside that plane. So the line that contains them, M, is also inside that plane. So we need our postulate that says if I have 2 points in a plane, then the line that contains them will also be in the plane. That looks like it's going to be this one right here, postulate 2.5. The next one states that the intersection of planes R and S is line M. So again, in this picture, I've got that plane R. I've also got a second plane, plane S. The place where these two planes come together is this line, line M. All right, let's find ourselves a postulate that goes with that. I know that's the one way at the end. I remember that picture. If I've got two planes that intersect, then their intersection is a line. That's postulate 2.7. The next statement states that through the three non-collinear points, so I've got points C, D, and E. Notice D and E are collinear, but C, D, and E are non-collinear because all three of them are not on the same line. There exists exactly one plane. In this case, it looks like that plane would be S. So find a postulate that says that. It looks like it's going to be this one, 2.2. Through any three non-collinear points, there's exactly one plane. And I have one more left. Plane S contains at least three non-collinear points, C, D, and E. So it's going to be the last postulate that I have not used. This one right here. A plane contains at least three non-collinear points. And again, this is not a skill that I expect you to do on like a quiz or a test because I don't expect you to have these numbers memorized. Like, I'm not ever going to say postulate 2.7 and expect you to tell me what 2.7 is. We're just doing this activity now as notes because we have these definitions in front of us. All right, so now a little practice applying these definitions, and hopefully this isn't a huge new skill for us because we're kind of familiar with these postulates already, even though we didn't formally learn them until today. Looking at a geometric picture, I'm going to identify what information I can assume to be true and what information I cannot assume to be true. So we could put a ton of things in these boxes. We're just going to pick out a couple though. So things that we can assume to be true. If anything is on a line together, we can assume that those points are collinear. So let's pick some points on a line. It looks like F, H, and B are on a line together. So I'm going to say those points are collinear. We can also assume that points on the same plane are coplanar. And all of the points here lie on the same plane. So let's just pick some of them. I'm going to say point G, point C, and point D. But again, you could pick any points on this plane. Other things we can assume, we know vertical angles are always the same. Remember, vertical angles are angles that are across from each other when two lines meet. So I'm going to pick two vertical angles that we can say are the same. Let's look at this angle here and this angle here. It looks like one of them would be HJE, and another one of them would be CJD. And then another thing we can assume is that linear pairs are supplementary. Remember, linear pairs are formed when you have a line with a ray coming off of it. So these two angles form a linear pair, and they're supplementary, so they add up to 180. Let's call the angle on the left, I kind of covered it up, but it's FHA, and the one on the right we'll call BHA. So again, there's more things that we could assume, but those are kind of the basics. If you've got points drawn on the same line, they're collinear. If you have points drawn on the same plane, they're coplanar. If you have vertical angles, they're congruent. If you have linear pairs, they're supplementary. All right, things that we cannot assume. It's kind of the opposite of the things that we can assume. So maybe let's clean up this picture so we can see it a little better. You cannot assume that points not drawn on a line are collinear. So even though, like these points here, G, F, and E, look like they line up, like they might maybe be on a line together, we cannot assume they're collinear unless there's a line drawn there. Another thing we cannot assume that any segments have the same length unless they are marked as the same length or unless it's told to us, like written out in words. So I know that segment FB and segment EC look like they might be similar lengths. We cannot assume they're congruent unless we are specifically told that they are congruent. So something that is not true would be that FB is congruent to EC. Another thing we cannot assume to be true are angle measures. Again, unless they're like specifically told to us in words or if we've got angle measures written out in definitions. So I know that it looks like I've got right angles here, but we don't know that for sure. So one thing that I cannot assume is angle AHB is a right angle. Or actually, I'll write that in a different way. I'm going to teach you a new symbol today. If I have two lines that are perpendicular that meet and make a right angle, we've heard this word before. I've just never showed you the symbol. So we cannot assume that line AH, actually I'll say segment AH, is perpendicular. That's the sign for perpendicular. It looks like an upside down T to HB. And again, these are things we cannot assume, so maybe they would be true, but we don't know it for sure. And while we're doing symbols, I'll teach you another symbol. These two lines, we'll say segment FB and segment EC again, look like they don't ever intersect, or they look like they're parallel. Again, that's a word that I think we've heard before. But we don't know that for sure unless it's specifically told to us. So I'm going to say another thing we don't know for sure is that FB, I'll call it a line this time, is parallel. The symbol for parallel is just parallel lines to EC. Again, there are a ton more things I could have put on this list. These are just a couple examples.